Welcome back to Advanced Functional Programming. I'm Daniel, and in this video we're going to start discussing functional collections. Now, what do I mean by that? You'll see in a second. So let's do a small mental exercise. Let's consider sets for a moment. So sets, as you already know all too well, are collections of elements and they do not contain duplicates. Now, sets, as you already know in Scala, are callable in the sense that they have apply implemented. So you can call, quote-unquote, call a set with an argument, and it will return true or false depending on whether the argument is in the set or not. So for all we care, set instances are callable like functions, and the apply method always returns a value true or false depending on whether the argument is contained in the set. So we might think that sets behave like actual functions. Now, if you take this mental experiment a little bit further, I would like to propose to you the enormously outrageous idea that sets are actually functions. And if you're curious enough to take a look into the Scala official documentations, you'll see that the trait set actually extends A to Boolean. Take a second to think about this. Such a well-known collection is actually implemented as a function. This is functional programming. We can implement collections as functions. Now, let's get back to the IDE and let's play around with this idea, and we'll reach some pretty interesting conclusions. Alrighty, we're back in the IDE, and this time I want you to go to the exercises package and right-click and click on New Scala class, and I want you to create a trait, and I want you to name this mySet. I want you to go ahead and implement a simple trait which extends A to Boolean. So as an exercise, I would like you to implement a functional set. In particular, I would like you to implement an apply method. So the apply method is already contained in the A arrow Boolean trait, so that's fine. I would like you to create some other methods that are very collection specific. For example, contains, which returns a Boolean. This will be very simple. Adding an element, and this will return a new mySet. Concatenating another set. This is also known as union. This is a mySet A. And it will return a mySet A. And then I would like you to implement the classics, map, flatmap, and filter. F from A to B. So we needed another type parameter B. So the function here will be from A to B, and the result will be a mySet B. Flatmap, which receives another type parameter B and receives a function from A to mySet B. And at the end will return a mySet B. Then filter. This is going to be very interesting when you implement it, because it's already an A arrow Boolean type hint, and this will return a mySet A. Okay, and finally, I want you to define a method for each, which takes a function from A to unit, so that we can print all our elements. All right, so in the first stage, I want you to implement a little mySet trait with all these methods. You can use list as an inspiration for this set. You can implement this as a cons-based set or as a linked set, if you will. But that's just an implementation suggestion. You can implement this as you want. So pause the video and try this out and implement this for yourself and see how this works like. And I'll come up with solutions in just a few moments. All right, so let's see how this works. I'm going to take the cons-based approach. That is, I'm going to implement a singly linked set. For that, I'm going to implement two subclasses of this mySet trait. I'm going to implement a class called emptySet with A extends my set A, mutable my set, of course, my set A, and a class non-empty set in the same fashion as we did for lists. That is, I'm going to say that this guy is a head and a tail. And the tail is a my set A. This also extends my set A. Now, the reason why I chose empty set to be a class and not a singleton object extending my set nothing is that if you paid close attention, my set is not covariant, it's invariant here. You can make this covariant if you want, but this is not the focus for this exercise, and I'm going to refactor empty set in later stages of this exercise anyway. So I'm just going to consider empty set to be a class, and I'm going to implement the method inside. Cool, so let's implement all these methods in both of our classes. I'm going to start with empty set because it's so easy. Now, of course, my set extends a boolean, which means that it has an apply method that I'm still going to need to implement in each of the classes, but I'm going to implement it in the trait itself. And I'm going to say that the def apply with element of type A returns a boolean, and its implementation is contains. So this is the general contract of the mySet trait. The apply method will only tell if an element is in the set or not, and it will return true or false. All right, so let's roll our sleeves and actually implement all these methods in empty set and non-empty set. So let's start with contains, which for empty set is super easy and will return false. There is no element that is contained in the empty set. Adding an element will return a non-empty set, with the head being the element that we pass in as parameter. So element, and this as the tail. Concatenating another set to the empty set will just return that set. So I'm just going to return another set, because empty plus whatever is whatever. So the result here will be another set. And then the classics map, flat map, and filter just won't do anything. It will just transform an empty set A into an empty set B. So mapping an empty set with a function that turns from A to B will just turn this into a new empty set B. Flat mapping will do the same. And filtering will just return this because there's nothing to filter. And for each, just won't do anything, and it will just return the unit. If you remember, the unit value is this little guy, parenthesis, parenthesis. All right, so that was super easy. And as you see, the empty set isn't read anymore because we've implemented all the required methods. Let's go to non-empty set and implement those as well. So we only care about these 7 methods from contains to for each because the apply method here was already defined in the mySet trait. All right, so let's define our methods here. So let's start with the contains function. The contains function is the crux of our non-empty set, and it will say whether an element is contained in this non-empty set. And the implementation is going to be fairly simple. So we'll say that the element is contained in this set if it's equal to head or if somehow tail contains it. So the implementation it contains is going to be element is equal to head or tail contains element. And contains, all right. So this is going to be the entire definition of contains for the non-empty set. Now, adding an element, we'll need to check whether the element is already contained. So if this contains element, then I'm just going to return this same set because I don't need to add it another time. So otherwise, I can add it into a new non-empty set of type A, of course, with element and this as a tail. All right, so if I already contain the element, I'm returning the same instance. Otherwise, I'm returning a new non-empty set with the element as the head and tail being this non-empty set. Now, the concatenation function is going to have a super one-line implementation. Watch what I'm about to write. So I'm going to say that because this is a non-empty set, then the tail exists and is also some form of set, either empty or non-empty. So I'm going to say tail plus another set. So I'm recursively calling the ++ method on tail, and then I'm going to add the head. Funky, right? This works because of recursion and because of polymorphism. So if I have, for example, let's just break it down real quick. So if I have the set 1, 2, 3, and then I do ++ set 4, 5, then by the nature of this implementation, this will be the tail of the first, so 2, 3, ++ 4, 5, plus the head 1, which is recursively going to be the set composed out the element 3 ++ 4, 5 plus 1 plus 2, which is going to be the empty set ++ 4, 5 plus 1 plus 2 plus 3. And the concatenation here for the empty set is going to be the other set. Notice the implementation right over here. So this is going to be the set 4, 5 plus 1 plus 2 plus 3. So the set 4, 5 is just going to add the elements 1, 2, 3 in order. So that's going to be the set 4, 5, 1, 2, 3. Remember, we don't really care about the ordering of the elements. We only care that the contract of the set is met. And don't worry, we're going to write some test code here as well, just to prove that our method implementations are correct. But let's just finish them up. So map, flat map, filter, and for each. The map is going to be fairly simple. And because this is a non-empty set, I can recursively call map on tail. So I'm just going to say tail map f. And then I'm going to add the application of f to the head of this list. All right, so let's put the proper parentheses here. So tail map f will apply the function f on the tail of this set, and then I'm going to add the application of f to the head of this set, and at the result, I'm going to get a mySetB. For flat map, the implementation is going to be fairly similar, only the operator at the end is going to be different. So again, because this is a non-empty set, I can apply flat map to tail. So I'm going to say tail flat map f. And then instead of adding f head, I'm going to concatenate f head. Because remember, f head just returns another mySetB, so it makes sense to concatenate that. Now, filter is pretty interesting, and I'm going to open some curly braces because I'll define an auxiliary value here called filtered tail, which is the application of filter on the tail, so tail filter predicate. All right, and I'm going to return the following expression. If the predicate holds for head, so if predicate head returns true, then I'm going to return filtered tail plus the head, because the head passes the predicate, so it makes sense to be contained in the result. Otherwise, I'm just going to return filtered tail. Okay, and finally, for each. For each is going to be fairly simple, and it will apply f to head, and then it will call for each recursively on tail. So tail for each f. Cool, so we've implemented all the methods in both classes, so both empty and non-empty set are not read anymore because we've implemented all the required methods. But before we go about testing the code, let's create a companion object for mySet just for the convenience of building sets. So let's say we define a companion object called mySet with a method called apply, which will take a type parameter a and some elements or values of type A, and I'm going to create a var_arg method by saying values are a star. That is, I can provide multiple values of type A here, and this will return a mySetA. And to implement this, I'm just going to call an auxiliary function that I'm going to define inside. Let's say this is called build set from a sequence of values. So value sequence, which is a sequence of A, and some accumulator, just to make this build set function tail recursive. So an accumulator will be my set A, and the result will be a my set A. And the implementation is going to be simple. If value sequence is empty, then I'm just going to return the accumulator. Otherwise, I'm going to call build set recursively by saying values valseek tail and accumulator plus, notice the plus operator that we defined on my set, plus valseek head. All right, so we're fine to annotate this little auxiliary function with @tailrec. All right, and as a result, to apply, we're just going to call build set by saying values dot to sequence. So values is a collection, but it's a var arg collection, so it needs to be converted to a sequence. And as an accumulator, we're just going to pass in a new empty set A. Now, I know I went kind of fast with this implementation, so if you're unsure how the apply method actually works, let's break it down real quick. So when I say val something equals my set 1, 2, 3, that actually calls the build set auxiliary function with the sequence 1, 2, 3 and the empty set as an accumulator parameter. And because build set is recursive, it will say, is valseek empty? Well, no. So it will return build set with the tail of the sequence, so with the sequence 2, 3, and accumulator, which is this guy, plus the sequence's head, so the empty set plus the element 1. That in turn calls build set recursively with the sequence just with the element 3 and the set with the element 1 plus the head of the previous sequence, which is 2. And then another recursive call with build set with an empty sequence and 1, 2 plus the element 3. And now because the sequence is empty, it will just return whatever it is stored in the accumulator here, which is the set 1, 2, 3 as desired. All right. Now, having this defined, let's go ahead and create a little test app. So I'm going to say object, let's call this my set playground extends app because we want our code to be runnable. And let's test our functions. So let's say that I have a small set, which is my set with, let's say, 1, 2, 3, 4. And let's print all the elements in this set. So s for each print line. So I should see the numbers 1, 2, 3, 4 in some order. In particular, I see them in reverse order, but I don't really care. This is a set, not a sequence. So all we managed to specify here is that the apply method for my set works correctly, and the plus operator works correctly because the apply method relies on it. Cool, now let's play around. So if I add another element, say the element 5, and I run the same code, I should see the element 5 in the set as well. So I see the element 5 here as the head, which is good. If I add another set, let's call this my set with, let's say, -1 and -2, then this guy should work as well. So I'm seeing the -2 and -1 elements added to the bottom of the set. This is interesting. Also, if I try to add an existing element, say element 3, I should not see it twice. So let's run this again. So as you see, 3 only occurs once. So this is good. The set apparently keeps its contract that it only contains each element once. Now let's play around with mapping and flat mapping and filtering. So if I do map, and for every element in the set I say multiply it by 10, and then I do for each print line, then I should see all the elements with a 0 at their end, of course. And if I flat map, with each element generating a new set of its own, let's say it generates the set contained of the element itself and 10 times the element, then I should see both 1, 2, 3, 4, 5, minus 1, and minus 2, and their multiplications by 10. So if I run this again, you see them all in here. So minus 10, 1, minus 20, okay, everything works correctly. And then if I filter, let's just filter only even elements, I should not be seeing the 5 and the 3 and the 1 and the -1. So if I run this again, I should only be seeing even values here. Right. All right. And with that, with just basically one line, we've tested essentially all the functionality that we've written in this video. So I want you to take a step back and have a look at the kind of code that we wrote in this video. If you think about it, we implemented a collection without thinking of it as a collection, but rather as a function, as a property. This is a new, different thinking style that I wanted you to get familiar with in this video. So this is the skill that we're practicing, a different kind and a different way to think and approach code. So now that we've got a good foundation of our little functional set, we can go even a step further and enhance this as a truly property-based collection, and we'll get to some really interesting places. So let's take a small break and join me in the next video where we'll level up our functional set. So see you there.